Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, How PSM Programs of the Past Should Shape a Better PSM Future. Our speaker is Patrick Nonhof. Patrick Nonhof holds a BS in Chemical Engineering from the University of Texas at Austin. He has nearly 20 years of experience in the petrochemical industry. He began his career with BASF and held positions in project engineering and operations. After BASF, he worked for Berwanger, Inc., an engineering consulting company based in Houston. In 2006, he co-founded Provenance Consulting, LLC, a process safety consulting company. Provenance's focus is implementation and maintenance of PSM systems with a focus on data management. One quick note before I turn the session over to Patrick Nonhof. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Patrick Nonhof. Hi, Patrick.
Hi, thanks for the introduction, Pamela. I appreciate that. Thanks for everyone that's attending. I look forward to sharing a little bit of information with you, and hopefully you walk away with a little more knowledge than you came with. As Pamela mentioned, we're going to talk about how the PSM programs of the past can help shape the programs in the future and even arguably maintain the existing programs a little bit better. Some things we're going to discuss. I'm going to talk about the brief history of PSM implementation, mainly just to get everyone to the same playing field. There's probably a lot of different levels of expertise on the call, and I want to make sure that we all start from the same foundation. So I'm going to provide an overview and context of PSM implementation, and then some of the things that resulted from that implementation, the PSM landscape that we're currently living in. After that, I'll talk about aspects that make successful PSM implementations. And I've really categorized it into 4 different components that I think are frequently underemphasized or mismanaged during PSM implementations and management of programs. When I go through those, I'll describe each of those 4 components, and then I'll go into a detailed example for each of the 4 to kind of demonstrate if they would have followed one of these 4 components, they could have avoided some problems. And I'll talk about some very specific problems. And then I'll say what we can do using these 4 components moving forward. There's obviously some emerging PSM programs at all times. The one that I'm going to talk about today is the Independent Protection Layer, IPL's Lifecycle Management. Over the past 10 years, there's been new PSM programs that kind of come and go. Risk-based inspection is one, and the one that I think is really interesting now is that IPL Lifecycle Management. So, some history about PSM. There's always differences in what PSM, how PSM is defined. I think a typical definition is a regulation passed by OSHA in the early 90s to prevent the release of highly hazardous chemicals. There's 14 elements to any good PSM program, and that's kind of a stock regulatory answer. I think a more practical definition is, and the way I like to think about PSM is it's really an interwoven series of programs, practices, systems, software, and people that are focused on understanding and mitigating the risks posed by highly hazardous chemicals. So we all ultimately want to make sure that we don't have any significant and catastrophic releases, but really it's a series of programs, and if you think of PSM, a handful of pillars of different systems that are all under the PSM umbrella. So when it was implemented and passed, individual departments really were assigned the task to implement PSM overall. And what you experienced in the past 20 years is the implementation really occurred by a series of different groups. So you could have your inspection department that went out and implemented an inspection data management system. So they said, hey, we've got to go inspect all of our fixed equipment. We have to go take thickness readings. So we're going to implement a system that tells us what the minimum thickness is and what the next inspection interval needs to be. The PSM department frequently were chartered to update all of the drawings and documents that were PSM related. So PNIDs, PFDs, plot plans, and generate PSM procedures. Engineering departments had to generate release system studies to make sure that the release system design and flare tips and radiation levels from the flare all met the standards that were in industry. And then maintenance departments had to implement maintenance plans and schedule maintenance routines and generate procedures. So you can start to see that PSM isn't just one component of an organization. It's just not one system, one process. It's it's really a series of different components, processes, and systems. And as I like to say, it's really interwoven. So how did that leave us? Where are we now? Well, where we are now is we have lots of different systems and processes and databases, and similar process safety information, PSI, resides in all these different systems and applications. And that's really across many different departments. And today, each system, software, and application, they serve a purpose, and they must be maintained. You can't arbitrarily eliminate one. So if someone came to you and said, hey, we have all of our pressure vessels listed in our inspection data management system, oh, and we also have all of our pressure vessels on our P&IDs, I think it would be clear that just because we have similar inventories and listings in those two systems does not mean we could get rid of one or the other. They both serve a distinct purpose and must be maintained. However, during the implementation and when every system was implemented, there was some unintended consequences. One was redundancy of validation efforts. So in order to implement a system, you have to go out and validate certain information, whether that be walking down P&IDs, confirming equipment information. And since everyone did it individually, for the most part, there was a lot of redundancy of efforts. Each effort really resulted in isolated data silos that is stored and maintained separate from each other. And what's kind of even more unfortunate, they weren't structured to benefit each other. So you might have all your maximum allowable working pressures, MEWPs, for all your vessels in multiple locations on your P&IDs, in your inspection data management software, as part of your release system design. And that's just kind of how things grew. They grew organically by each individual department, and that's where we are today. One other unintended consequence was associated with PHAs. And I think unintended consequences are oftentimes looked at as a negative, but I think this is actually one real positive one. If we were honest with ourselves and we said 20 years ago, we're going to perform these PHAs, I would argue that most people would say we're doing it because there's a regulatory requirement here. But I think that what we're finding is that the information and documentation that are generated as part of PHAs are incredibly valuable, and the information and that data, the value that the PHA generates was probably never predicted to the level of what it's generating now. It is incredibly valuable, and it's leveraged in many, many different ways. That's actually one of the things I'll talk about a little bit later. So that's kind of the general PSM landscape now. Implementation by a series of different people, resulting in lots of different data silos, revalidation of efforts, and there's some inherent goodness with that and some inherent problems as well. So if we were to scale it back 20 years and say, hey, we want to start over, what would be some of the practices that were really underutilized and maybe overlooked that could create even more success than what we're experiencing now? I've broken it down into 4. There could be probably many, many more. There's a whole litany that you could probably put together, but I listed 4, my top 4. The first is ensure supportive participation and culture whenever you're implementing a PSM process or maintaining a PSM process. Define and determine the scope. So what are you trying to implement? Define and determine that scope. Understand the data that you need to implement that PSM process. Understand the data and then what makes that data right. And I'll talk about each one of these in detail. And then the last, I mentioned it earlier, leverage the PHA. So the PHA meeting and documentation and results are incredibly powerful, incredibly useful, and I think that if we were to do everything over again, we probably would leverage the PHA much more than we currently do. The other thing that I think that is important when you think about success is it must be contextual. You must evaluate how your particular PSM program that you're implementing fits into the larger overall PSM umbrella. So if you're implementing mechanical integrity, or if you implement independent protection layer, lifecycle management, which is kind of the emerging topic that I'm going to focus in on, you need to understand how that fits into the overall PSM umbrella. And if you miss that contextual fit, I would argue you won't be as successful as you could be otherwise. So these 4 components that I mentioned earlier, they all have a common thread. And as I go through it, I want you to kind of think about what these common threads are between these 4. One is upfront and ongoing participation from key stakeholders and facility experts. And one of those things is not just to get it right, but it's also to feed efficiency. So you can imagine if you started to implement a program back in the 90s, or heck, even now with one of these emerging PSM programs, and you don't get the right input, and then years later someone comes along and notices that they left out some scope or they did a process incorrectly, you may have to rework an entire process for a facility. So it's very good to have the right people involved, not only for buy-in and culture, but because it makes you much more efficient. You will really minimize and reduce potential rework. Another critical aspect of successful components of a PSM implementation is to leverage what you already have. There's a lot of data that's already gathered, frequently already validated, and you don't need to go reinvent the wheel. If you've already validated the information that you're going to use for your process, make sure you know where that information is, how it was validated, and how you can use it. And then the last is kind of a basis for establishing your PSI. When you have to evaluate it, it's all based on data. So it's all based on information. When you're implementing a process safety management system, it's data-based. Very frequently, equipment-based, equipment-centric. And that information that's associated with each piece of equipment, there is a lot of necessity to have information about each item. And you need to define what is correct as the as-built condition. And I'll talk about that in a few of the following slides. Real quickly, I've talked about the different systems that have been implemented, and I've mentioned this emerging process in practice is the IPL Lifecycle Management. So as part of PSM kind of continuing and growing, I'm going to use this as an example to show you how to apply the 4 different components that I think breed success in PSM implementation and maintenance. So just to get everyone on the same page, kind of similar to what I did to PSM history, when a PHA is held, you frequently identify different scenarios and the risks, and then you identify how those risks can be mitigated. And the way you identify the risks are through causes of abnormal operation and the consequence, and then you look at what safeguards and independent protection layers you have to protect against certain consequences. So you come up with a risk ranking, and then independent protection layers and safeguards are used to reduce the risk. Those IPLs and safeguards then go through a life cycle management, and a lot of facilities and organizations are really now getting their hands dirty in this life cycle management. So they take those PHA safeguards, and then they feed them through a functional safety assessment to make sure that the way that the PHA understood the response is accurate. Then they perform some SIL, safety integrity level calculations, to make sure that they will be as reliable as you would need in that particular scenario. If it's satisfactory, you kind of move on. If not, you redesign it potentially. Let's say it is satisfactory. You'll create safety documents. You'll perform some visual inspections. You'll document and schedule those inspections. And then you also generate some proof tests and perform those proof tests. So there's probably quite a few different life cycle managements that can be put together in a workflow, probably quite a different number of perspectives of what the right order is. But I just want to kind of give everyone a flavor and bring everyone to the same kind of level playing field of what lifecycle management is for an IPL. It's really identifying things that reduce risk and then maintaining them, setting up procedures to maintain them, and ensuring that they provide the appropriate risk reduction. Okay, let's go into the 4 components of successful PSM implementation. The first is employee participation. This is actually one of the 14 elements of the PSM standard. And this is the only one that I correlated directly to a PSM element. And I think this is much more than just compliance. Whenever you talk about employee participation, this is not just the regulatory and kind of obligatory, hey, make sure you have the right attendees in a PHA. Let's make sure we have an operations representative and a process engineer and someone that understands the hazard analysis techniques. This is much more about just the obligatory attendance in a meeting. This is about setting your culture. This is about buy-in from the right people. And this is really something that has to happen at all levels. I think frequently people talk about management buy-in to PSM. I don't think that enough attention is given to some of the other levels of the organization, the technician level, the operator level. Generally speaking, I think everyone sees the value, but they only see the value after it's been explained and after they understand it. I think a lot of resistance to PSM programs is due to lack of understanding. They don't understand why they're doing certain things, why they're being required to do certain things, but with that understanding comes acceptance and even support. So one of the things I've always considered is when I've been part of an implementation or maintenance of a PSM element or program is that teaching is a critical aspect of that implementation. So you're there to teach people how it's going to impact them, how they need to maintain the system, and how it's going to impact their daily operation. So a specific lesson of employee participation. Here is a two-phase separator with a level control valve that's feeding a downstream vessel. So you have the two-phase separator, you have liquid coming out the bottom, high-pressure gas going out the top. It operates at 220 pounds. The downstream vessel is only rated for 200 pounds. So one of the frequently evaluated scenarios is what happens if that control valve fails open? Well, that is actually evaluated in a couple different ways. One, it's evaluated as part of the PHA. And as most people on this call know, PHAs take a very risk-based approach to evaluation of scenarios. They try to assess the risk of something going wrong, and they focus on the risk. So when a PHA looks at this, they may say, oh, well, if that control valve fails open, then we might lose the liquid level in the upstream vessel, and we could have what they call gas blow-by, so high-pressure gas blowing through to the downstream vessel that normally doesn't see that high-pressure gas. Well, if it's operating at 220 pounds upstream, and the maximum allowable working pressure downstream is 200 pounds, then you're arguably going to overpressure the downstream vessel. However, in a PHA, they may say, hey, the operating pressure does not significantly exceed the MAWP, so there is no consequence concern. Even today, a lot of operating companies are moving towards thresholds of overpressure in their PHA evaluations. So until they exceed a certain threshold of MAWP overpressure, they don't have any consequence of concern. Well, what will that do? That will result in the PHA saying, oh, there's really no significant risk if that control valve fails open, at least no hazardous risk. It may be an operability nightmare, but it's no hazardous risk. And so therefore, they may not have any safeguards or IPLs if they're just focusing on safety and environmental impacts because there's arguably no loss of containment. However, another part of the PSM umbrella would be the release system design. And frequently, they will look at control valve failing open. And when you perform a release system design review, this is much more standards-based, kind of prescribed methods of engineering evaluation. So what they will see is that the scenario will exceed the downstream MAWP. So if this occurs, we will exceed the MAWP. When that occurs, the regulations and the requirements and the design standards tell us you shall design a release device to account for this overpressure scenario. So they would size it, they would look at it, and if they had any type of design concerns with that release device, they would go out and fix them. Now, the logical question you might have is, how in the world does this have to do with employee participation? Well, management will see both of these evaluations, and they will see the results of both evaluations are different. The employee participation doesn't necessarily mean participation in the evaluation. It means participation and understanding of what these evaluations will deliver. And so you can imagine some engineering manager receiving an engineering package saying we've got to redesign a relief device. And he says, okay, well, that makes sense. What was the scenario? It was inlet control valve failure. And then he's just kind of curious. He's like, well, that sounds like we're going to spend some good money. I better go see what happened in the PHA. He goes and looks at the PHA, and this exact scenario says, don't do anything, arguably. So it starts to show some inconsistency in evaluation. Employee participation won't drive that out, but the greater you have employee participation understanding what individual implementations will deliver, the more they will understand that they may not always be the same, and that that is okay, and that the purposes of the evaluations could be different. So you need to have buy-in and understanding to make sure that the results can be used properly. Okay, so now how can we apply the component of employee participation to this new and emerging topic, IPL lifecycle management? Well, when you start to look at the IPL lifecycle management, you're going to start to plan maintenance for all of these different IPLs. And you need to start to involve all levels of maintenance from management through the craftspeople in the planning phases. One deliverable of this is going to be testing regimes for all of your IPLs, potentially all of your safeguards. And for the most part, these are instrument-related type of devices. So basic control, loops, alarms, safety instrumented systems. And so you're going to set up testing regimes. So how often you test it will be driven by what reliability is required to mitigate the scenario. And you can imagine if you don't have the right people involved, you're now testing quite a bit of new stuff that you didn't test previously. That may require additional resources that you don't currently have. So if you were responsible for planning this IPL lifecycle management, you came up with all these testing regimes, and you just delivered it to the maintenance department, and they didn't have any awareness, all they know is that they've been dumped a bunch of work that they didn't participate in planning. That's not going to go over very well. So the earlier you involve them, one, you'll get better deliverables. You'll know what the testing regime needs to be because, frankly, they've probably tested it before. They know where it fails. They know how to test it. And two, they can adequately staff for it. So that's part of the employee participation that I recommend in this area. Kind of the second successful component of PSM implementation is define and determine your scope. Scope can be subjective, but as time, it is prescribed. So what factors do you need to take into consideration? So if you're looking to implement a system or a process underneath the PSM umbrella, you need to make sure you define your scope well. That may well be all equipment that is in a PSM-covered process. It may be equipment that's in critical systems. It may be some other definition, but it needs to be determined. And the way you determine it is you involve key department representatives and customers in that discussion. And not only at the beginning of the discussion, but throughout the implementation. That helps to obtain facility-wide buy-in for the scope and strategy of the implementation. So again, it kind of ties into the previous component, which is get the right people involved. And it also increases the efficiency later on to make sure that your breadth of scope is properly determined. So one thing I want to emphasize is don't confuse defining the scope with determining the scope. One thing that I think is frequently overlooked is if you decided you wanted to define the scope as all pressure vessels that contained highly hazardous thresholds of chemicals. That's a great definition, but then you got to determine what pressure vessels fall into that category. Well, the way you would do that, you could say, well, just give me a listing of all of our pressure vessels. Well, that may not be as easy as you think. So one thing you may have to do is verify your equipment inventory, and you can accomplish that by cross-checking them against the systems you currently have. Let's say that you were chartered with implementing mechanical integrity for fixed equipment at a midstream facility. Well, you may want to implement mechanical integrity for all fixed equipment that has certain thresholds of chemicals. Well, just getting that list may be difficult, and you may need to go to the different systems and repositories to generate a comprehensive listing. So check in between your systems to generate the reliable inventory, and you may find there are some system inconsistencies that will need to be resolved. Multiple approaches are available to generate that inventory. One would be simple Excel spreadsheets, do a dump from different data repositories and compare them, and you can have a resulting scope, scoping list. You can also use some commercially available applications to do that. So, one specific lesson in defining and determining your scope. Release device studies. Frequently, release device studies are contracted out. So they want to do a comprehensive facilities evaluation for all your release devices. They'll frequently just send a list to a contracting company and say, hey, give us a quote and a work scope to perform this evaluation for our entire facility. Well, you need to really be careful that you don't understate the work and that you also don't overstate the work. One example would be if you just simply take a listing of all the release devices from, let's say, your financial system like an SAP, and you send it and say, hey, please give us a scope of work and a cost to perform evaluations on all these release devices. What you may not know is that the release devices that are on the hot water heaters in your office buildings are part of that list. And now you're asking an engineering firm to perform a study on, frankly, a pretty standard release device that you may not want to spend the same effort and energy in evaluating as you do on one on your debutanizer column in your facility. That's an example of overstating the scope. An example of understating the scope would be if you only provided a list of release devices to be evaluated. Well, frequently there's vessels in the facility that aren't protected. That doesn't mean you don't need to study them. You still have some regulatory obligation to document why a release device is not required. So if you just simply say, hey, study all these release devices, and then you don't document why certain vessels don't require a release device, you're arguably still out of regulatory compliance. So how would this component number 2, define and determine your scope, impact the emerging topic of IPL lifecycle management? Well, one question that I frequently see raised is, what do we need to include in this lifecycle management? Is it all safeguards identified in a PHA? Is it just the IPLs that are generated out of a LOPA study? Should we list additional IPLs in a PHA or additional safeguards that we don't need for risk reduction? And then what do we do with that list? So ultimately, you're going to have to select and choose what devices you're going to maintain, what IPLs you're going to enter into this lifecycle management. And it could be all safeguards in a PHA. It could be all IPLs. Here's another kind of interesting situation that will arise. You may perform your PHA, you may even perform a LOPA, and you could have a safety instrumented system in your facility that the PHA and the LOPA do not take credit for. What do you do with that safety instrumented system that already exists? Do you now not maintain it at all? Is that in your scope? Is that out of your scope? It wasn't used by the PHA or LOPA. Do you need to maintain it, and if so, how? So all these questions need to be answered. That's what sets your scope. The third component of a successful PSM implementation is determine what PSI is required, where it exists, and how to validate it. So one very effective way to determine those 3 components is to perform a pilot study or a proof of concept. And that's not to determine, are we going to go forward with this effort? It may well be, but most often it's not. It's really to provide a sound basis for the overall effort. What the cost, schedule, and scope is going to be can really be determined with a pilot study. It can be much more effective. It also allows you to determine what information is required for success. So if you are going to go implement a comprehensive P&ID walkdown, then you would need to understand, well, what information are we going to put on our specification blocks for our equipment? What are we going to show as far as piping? Are we going to have a threshold that we're not going to show any size below a certain threshold? We're not going to show any 1/4 inch tubing or less. So you need to determine all that, and this working through it, doing the pilot study, actually helps you determine and locate those questions that you may not otherwise ask. Also, if there's a specific software that you're going to leverage or utilize as part of that implementation of this PSM process, it allows you to vet it and test it. Frequently, those are chosen for you. Corporate IT comes to you and says, thou shalt use this software, and you're welcome. Well, frequently you need to use that software in order to understand what its strengths are and what its weaknesses are, and whether you might have to backfill its weaknesses and what its strengths really can be. So it allows you to really understand what the software is good at doing and where it may not be so strong. PSM implementation is really most efficient when all of that detailed data needs are understood prior to commencement of the implementation. This is very similar for chemical, since this is a chemical engineering audience. If you had a reactor and you didn't know your feedstock, how in the world can you predict your product? And feedstock of a PSM implementation is data. It's process safety information. And again, meet with the right people, understand the right data that you need, and make sure that you're gathering it correctly. Again, leverage your existing systems. You may already have a lot of this data organized and captured. But one thing that is incredibly important, ensure you put a process in place to validate the data that you're going to use. So, the accuracy of the data matters. And I will strongly encourage people, the correct value should always be determined as the as-built condition. And I'll go through a few examples in just a minute. So what determines the as-built condition? For a pressure vessel, it would be a U1 form or a nameplate. If you have a re-rate, it would be the re-rate calculations and the re-rate tag. And then identifying the appropriate validating records is critical. So simply because all your data systems have a specific value does not make it right. And I'll go through one specific example to where it's very obvious. So here's the example. Let's say that we were sitting back when we were just now implementing the PSM system, kind of an overarching umbrella of all things PSM, or we're setting a facility that historically wasn't PSM, but because of some potential future regulatory changes or changing of preference in the corporation, you now want to implement PSM at a new facility. Okay, so you have a pressure vessel, and its maximum allowable working pressure, its MAWP, is 450 pounds. 450. Okay, great. How did I get to that? Well, it came off of the U1 form, and it came off of the re-rate, not the re-rate tag, off of the nameplate. So we know that that is valid. This has never been through a re-rate. We can trust that documentation. So we know it's 450. Well, we have to implement it into our inspection software. So we're going to go through and we'll have a software. We'll implement it into the inspection software, and we're going to use 450 pounds, which is the right value. Well, as part of our ongoing PSM efforts that we historically have not performed, we're going to update the P&IDs. And the way we're going to update our P&IDs is we're going to walk down the P&IDs. We're going to put people in the field, boots on the ground, and walk down pipe. Well, when they were out there, as good field walk-down resources do, they look at the nameplates. And this gentleman looked at the nameplates and read it and said, oh, absolutely, and wrote it down incorrectly. So instead of writing 450, he wrote 540. Not too extreme of a mistake to make. So now the P&ID gets updated with MAWP of 540. Well, what can that lead to? Well, let's say that now you're going to do a release system evaluation. Frequently, release system evaluations are based on the P&IDs. So you deliver the P&IDs to the release system engineer, and we say, go. Go do your thing, sit in your cubicle, and calculate. And so they start cranking through the calculations, and they refer to the P&IDs, and they see that the MAWP is 540 pounds, which is wrong. And it's wrong because that's not the as-built condition. Furthermore, the PHA is performed, and they, again, use the P&IDs, and they evaluate all the scenarios, they evaluate all the risk, they evaluate the entire risk study using the wrong MAWP. What's even more frightening is they may even take action on it. They may evaluate it and say, well, if we overpressure, boy, we sure would like to have an alarm. Yeah, we all agree, let's configure alarm on that vessel. And where should we have that alarm? Well, we want an alarm 10% below the MAWP. Well, if you did that, you're still going to be well over the real MAWP. So you may even take actions that are incorrect. So I hope I don't have to tell you the results. The result and the problem is that that vessel, its structural integrity is only good for 450 pounds, but every other evaluation assumes it's good for 540. And all of this was caused by the simple switch of the numbers, and it's not too extreme. So why is this important? You got to make sure that you have a way to validate the data so that when you're implementing your release system, when you're performing your P&ID, you can say, hey, did this come from a bedrock document, and you can confirm it. Now, how can that play out in this emerging topic? So part of IPL Lifecycle Management is you may frequently take credit for an operator response to an alarm. So an alarm goes off, an operator is going to take some action to prevent this scenario from pursuing any further. Frequently, the response time is very important in determining whether that is an adequate independent protection layer or adequate safeguard. So if you don't have the right alarm value, you may be calculating an incorrect time. The pressure is rising at a certain rate. If your alarm is higher than what you think, when you get that alarm, you have less time to respond than what you actually think. So I will suggest, again, and emphasize, whenever using process safety information, use the as-built condition. Now, it's incredibly tempting to use other information when you're looking at IPL lifecycle management. There's been huge efforts to go through and do alarm rationalization and alarm evaluations at facilities, and they've generated immense amount of valuable data. And they'll say, hey, this alarm should be set at this value. Don't use that in order to determine whether your IPL is valid, because that change may be what you want it, but it's not currently what it is. And so all those other sources that could be tempting, I would encourage you not to use. Go directly to the DCS. So that is how you would apply component number 3. Make sure you understand the data you need, where it may exist, and then how to validate it. The fourth, and I mentioned this earlier, leverage the PHA. If we were to walk back 20 years in time, I think most people would argue, yeah, we understand the value of the PHA, but I think the true value that it's generating, that the discussions generate, that the documentation generate, was probably never quite expected. And I would argue on the good side. So the thing to consider is that the PSM implementation, the system you're implementing really needs to fit into the existing site puzzle, not only in the PSM umbrella, but how it interacts with non-PSM programs as well, but PHA in particular. One thing that's incredibly frustrating is PSM implementations frequently need lots of information from lots of different people. You need process engineering knowledge, you need design knowledge, you need instrumentation knowledge, you need inspection knowledge. And that's not just for PHA, that's for a lot of different process safety management exercises. So what's very frustrating is that you will frequently be implementing something and call on all these people and say, hey, when you operate this vessel, does it normally run at this level? Do you see any type of contaminants that could create a new corrosion mechanism? So you'll have a lot of the same questions that are already addressed in a PHA, or at least discussed. So the one thing that I would argue that makes very successful PSM implementations is to determine if the PHA has already documented what your implementation requires. A great example, risk-based inspection. One of the things they look at is different damage mechanisms that could occur to fixed equipment. And one thing that drives damage mechanisms is potential for impurities in feedstock. And if you have certain impurities, you could create new damage mechanisms. Well, in a PHA, they frequently talk about that. It's very frustrating. If you were just in a PHA 2 weeks ago, you talked about it, and now some mechanical engineer gives you a call and asks you about that all again. You've got to relive that one more time. So determine if the PHA has already done it. And if they haven't, then think, can you incorporate this discussion, this data need, into the existing PHA? Now, you need to expect pushback. People will say, well, the PHAs are already too long, already too boring, they're already too, too extensive. So you will probably get some pushback, but if you make the case that if you don't incorporate it into the PHA, you're going to have multiple meetings. You're going to have the PHA meeting, and then I'm going to pull the team that's very similar, potentially even the exact same, all back together again to generate the data that I need for my program. So, one specific lesson. This is real personal to me. Right after I graduated from college, about 2 years out, I was lucky enough to be part of a release system study. As you could probably see, I've scattered release system studies throughout my presentation. It's an area that I really enjoy. Well, the first exposure I had to release system studies was field verification. And I was asked to go out and field verify release device piping. So I was walking down the piping for each release device. And so this was on a Tuesday, and I remember it distinctly. It was about 2 o'clock. I just came back from a late lunch, and I was walking down a pipe. And I saw this gentleman about 20 yards ahead of me, and he was walking down some piping as well. Had a clipboard and a PNID, looked almost the exact same as me. So for about 20 minutes, I just kind of watched and kept on working and noticed that, man, we're walking down the exact same pipe. So I kind of went up and I thought, well, he's probably part of the same team. Tapped him on his shoulder and said, hey, you know, kind of noticed, should we compare notes? Should we try to help each other out? I said, what exactly are you trying to do? Are you trying to confirm everything for the release device study? And he said, oh, no, I'm not part of the release device study. I'm walking down this P&ID because they need it to be correct for the PHA. So he literally was walking down the exact same P&ID, the exact same pipe, making the exact same red lines as I was for two separate efforts. And so that's not leveraging the PHA process. If we recognize that, hey, we're going to walk down this pipe for the PHA process already and we're going to get this P&ID accurate, why not use it elsewhere? Now, how can we leverage that for kind of the IPL lifecycle management? Well, IPL Functional Verification is one component of that lifecycle management. When a PHA takes credit for an IPL, it also discusses how it should respond. So in the event of high pressure, this basic process control will receive a high pressure signal and it will close this valve. Or our safety instrumented function will respond in X, Y, and Z way. During the PHA, that is discussed usually pretty detailed. And a lot of discussion says, well, are we sure? They'll pull up loop sheets, they'll pull up cause and effect diagrams just to confirm that the IPL responds as expected. So one component of the IPL lifecycle management is to confirm that. And the reason that they are taking that additional step, I will argue, is because the PHA documentation sometimes isn't adequate enough to show that that has already been confirmed, or the PHA didn't confirm the functional requirement. So they'll say, hey, we expect the basic process control, and the PHA will say, oh, yeah, you know, the operator, and they'll say, oh, yeah, we get high pressure, and that closes. Well, later on, when they do the validation, they'll find out, oh, actually, when we receive high pressure, that doesn't close control valve 102 at all. It does something else. If that validation was just, I'll say, tacked on, if it wasn't already part of the PHA, tacked on to the PHA, you can imagine the efficiency savings. Because all you're going to do is you're going to go revalidate it after the PHA takes credit for it. So why not validate it then? Know what software you're going to use, how it needs that data, what format of data it needs, and then incorporate it into your PHA. So that's how to use and leverage component number 4. So those are the 4, and just kind of in summary, our past experience, it has to impact our future performance. If we don't take these lessons, and I've just taken 4 components, again, there's probably 10, maybe hundreds. If we don't, shame on us. So the 4 I have are ensure supportive participation and culture. Employee participation, it's the only one that I think is a specific element. Define and determine your scope. Don't understate it, but don't overstate it either. Understand your data needs and define what makes that data correct. Don't rely on just consistency. And then leverage your PHA. Is the PHA already generating some information I can use? Could we tack on the data generation as part of the PHA? Ask those questions. Well, I appreciate you letting me present, and I'll take any questions that you have.
Okay, thank you, Patrick. Attendees, you can direct your questions to host in the chat box, and I will ask them of Patrick. So first question, Patrick, you mentioned that you chose the top 4 components of successful PSM implementation. What would be the next few if you were to list a few more?
That's a good question. I think those 4, as you stated, are my top ones. I think the next one would be defining integration points with the MOC process. So after you perform an implementation, some flavor of the month for PSM implementation, of course, back in the 90s, it was mechanical integrity and release systems and PSI verification. Arguably in the 2000s, it was risk-based inspection. Now it's IPL lifecycle management. With each one of those, you need to understand how that's going to integrate into your MOC process. And the MOC process is fallible. It involves people. But the better you define what those interactions are and what should prompt MOCs and how an MOC could impact your system, I think that's probably the 5th. So my 5th would be defining those MOC interaction points.
Okay, thank you. Do successful PSM implementation programs typically have a dedicated PSM team?
So I can answer based on my experience. I think that having a dedicated PSM resource or resources lends itself to higher success rates. You have someone that's kind of monitoring the interaction between each of the systems, is monitoring the overall health of all of these different components that fall underneath the PSM umbrella. If you don't have that dedicated PSM resource or resources, what I tend to see is continued maintenance and operation in silos, that the mechanical integrity group maintains their system and the engineering group maintains their information, and no one's looking at how they impact each other. And really the health of your PSM program is measured by not only the health of each individual column holding up the overall umbrella, but really the interactions between each column. So I would say yes, success is related to dedicated resources.
Okay, thanks. Does IPL Lifecycle Management and RBI have direct relation in terms of integrity assurance?
Integrity assurance. I think I understand the question. I think that what they're asking is whether IPL Lifecycle Management, you're trying to ensure that you have some reliability of a response of your independent protection layers. Risk-based inspection tries to predict, based on risk, where you need to focus your inspection resources. They have a very similar flavor because one is trying to mitigate risk and one is trying to leverage risk to focus resources. So risk-based inspection will look at the risk if you have a certain damage mechanism, and if that results in a very high risk, such as the release of a very toxic chemical versus the release of, let's say, cooling water, you may want to focus your resources on that. So I think they have a similar flavor, but I think the end game, the results, are different.
Okay, thank you. If you were implementing an entirely new PSM program, where would you start and how would you prioritize implementation?
That's a good question. So as you probably saw, I emphasize process safety information quite a bit. So if I was to start from scratch and implement a new PSM program, either for a facility that just got built or for, let's say, a midstream facility that just kind of seemed to now be really taking on PSM for whatever reason, I would probably start with process safety information. So that is the foundation on which everything stands. So mechanical integrity, process hazard evaluation, all of those really kind of stand on the foundation of process safety information. So that's where I would start. Getting your PSI correct, your P&IDs, your equipment information, making sure that all that is validated and you have good processes to validate it. Make sure you have comprehensive and accurate equipment inventories. Do you actually know what all vessels you have in your facility? Do you know all the release devices? That's all PSI, getting all your PSI correct. Now, as far as prioritization, I would say it makes a whole lot of sense since PSM really is different ways to understand and mitigate risks. Find the riskier areas of your facility, so things with, very large quantities of highly hazardous chemicals or things that are extremely toxic, and start there. So start with process safety information, but maybe even more focused, prioritize based on risk of the facility.
Okay, thanks. How do human factors fit into your data-based PSM?
Well, I think the human factors kind of apply typically through a couple of different components. Human factors are usually most often considered in causes of failures, and that's typically encountered in the PHA process. So you talk about human factors and what could go wrong with the humans that are operating these facilities and maintaining these facilities. But I think where human factors could better be leveraged, and it really ties into point number 4, is once that's discussed in the PHA, is that leverage for other efforts? So let's say that there's a human factor that identifies something that could go wrong due to some interaction. of the humans with the equipment, and that results in an overpressure. That may not be an obvious overpressure scenario to a relief device engineer. So looking through the PHA system, the PHA database and documents, and then leveraging that information for other efforts is very critical. So I think human factors is important. Obviously, you got to capture all that. It's typically captured in the PHA, but then you need to extrapolate that to your other systems.
Okay, thanks. Should there be a different approach for new facility and old facility in managing IPL?
So while I used IPL lifecycle management as an example, I am not an IPL lifecycle management expert. There's people out there in the industry, they're probably well-versed, more well-versed than I am, but I will give you my opinion. The benefit that you actually have with an older facility is you have some really good data, depending on the age of the facility, of how reliability your instrumentation and safety systems really are. So you know that your IPLs and your lifecycle management need to achieve certain reliability. Well, you may have enough history and enough proven history to demonstrate a specific reliability. So I would argue that you could treat existing facilities slightly different because you have data on performance. Now, of course, vendors that generate and manufacture these components tend to publish reliability data, but they can't publish reliability data in your facility. Different mechanisms that could damage that instrumentation, or different operating regimes that could render it fallible. So I do think that you have an advantage, oddly enough, in an existing facility because you may have some, proven reliability data.
Okay, thank you. Can you discuss your views on RAGAGAP given the latest interpretations provided by OSHA, specifically the inclusion of internal company procedures policies as RAGAGAP?
So I guess, the current interpretations, there are some interpretations out there that saying that RAGAGAP does encompass internal standards. So if you have internal engineering guidelines that are exceeding the construction codes and recommended practices in the industry, you could find yourself in a position where you are, if you're not performing your engineering and your PSM practices to that internal standard, but you meet the industry guidelines, you could be in a position where you receive a citation. So my opinion on that is if you're a company and you're going to have these internal standards, you probably have them for a reason. And you've come to the conclusion that they're necessary for safe and effective operation. So if you're going to publish a standard, I can kind of see how OSHA would hold you to it.
Okay, thank you. I think that's all the questions we've received. Do you want to say anything in closing, Patrick?
No, I appreciate everyone's time. Thank you very much.
Okay, thank you. And if anyone still does have a question that they didn't get to ask, or they have something that they think of afterwards, they're welcome to send it to me at producer@aiche.org, and then I will forward it to Patrick. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Patrick Nonhof for this very informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this webinar or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.